Okay, welcome back to STEM Online Academy. My name is Jason Masterakos, for those of you who don't know me. And for those of you who don't know me, we are an advanced mathematics and physics uh, tutoring channel slash company, um, helping undergraduate students uh, get to the next level uh, by focusing on difficult exams slash contest problems. Okay, so what we're going to look at today is we're going to be looking at something very interesting. We're going to be looking at an ordinary differential equation that doesn't come up that often, but it's good to know how it works. Okay, just because it doesn't come up often doesn't mean it's not important. Okay, so the type of differential equation that we're going to be looking at, right, has to do with a linear algebra crossover. Yes, you've heard that right. There is linear algebra that is incorporated in this type of differential equation. Okay. And it's not always as straightforward. It can be a bit monotonous and annoying. Okay. And also sometimes conceptually tricky. And that's why I'm talking about it today. Okay. So uh, we're going to be looking at this specific differential equation. Quite often they're written when they have matrices involved, they're written in this form. Okay, I'm going to zoom in here on this guy. Right, it says the x prime vector is equal to some matrix A, right? A 2 by 2 matrix, by the way, times the column vector of x. Okay, where matrix A is a 2 by 2 square matrix with entries -1, 0, -2, 3. Okay. So I hope you have a background in linear algebra today because, yes, there's some linear algebra involved in solving this ordinary differential equation. Okay. So let's look at how we're going to solve this. Okay. But before I get right to it, let's get to where the main mistake uh, most students would have with solving this differential equation. Okay. And most students solve this system the same way, right? What I mean by that is they will just do a manual or algorithmic way of approaching it. They compute the eigenvalues, sorry, right? They get the eigenvalues, and then they're going to just write the exponentials, okay? Like the C1, if you know how homogeneous differential equations are formulated, they are in the form y equals C1 e to the lambda 1t plus C2 e to the lambda 2t, so forth, right? Um, But that's not good enough, right? They assume they understand the behavior just by writing out that formula. I mean, you can go through that algorithmic process, but you won't understand the behavior of the equation. Okay. Turns out the behavior is more important than just getting right to the formula, right? And that's what I'm going to talk about. Okay. So let's look at it. Let's look at doing the problem. Okay. So what we're going to do here is, right, is we're going to look at this through a geometric lens, not just algebraic. Okay. The mistake is thinking that the eigenvalues are going to tell the whole story of this problem. Okay, of this interesting differential equation. Okay. Uh, and they don't. Okay. They don't tell us the whole thing. All right. So step one to solving this ordinary differential equation, right? So we want to compute the eigenvalues carefully. Okay, very careful. Okay, so let's write out step one. Okay, so step one is this. Okay, step one. Okay, here's step one. Okay, we want to get the characteristic equation. So from linear algebra, you should know that a characteristic equation, right, right, from your linear algebra classes, is that a characteristic equation is written like this. Okay, it's the characteristic polynomial p subscript a as a function of lambda, right? is equal to the determinant, right? The determinant of A minus capital A being a matrix, okay? Square matrix, A minus lambda times the identity matrix I, and that's equal to 0, okay? Right? And what you would get from this if you were to input the matrix, right? I'm just going to go right to it here. You can verify on the way. You notice a mistake in the chat. I've already done this. That our p subscript a as a function of lambda is equal to, in the determinant form, negative lambda in the upper left corner of the determinant there, minus 2 on the other entry, 1 in the lower left entry, minus 3 minus lambda in the lower right entry, and this is all equal to 0. Okay? All right. So this is what we're doing right now. And since it's a 2 by 2 determinant, we just need to cross multiply the lower and higher entries and subtract. Okay? So we want to compute. Okay, so right here, we want to compute, right? Compute determinant, okay? So I am going to compute the determinant. Okay, computing the determinant is going to be negative, right? So negative lambda, okay, times negative 3 minus lambda, okay, minus 2 times 1, okay? That's what we have here. And this should all be equal to 0 on the right-hand side, okay? Right. And once you're able to clean up this mess, you'll notice that you're going to get this, right? You're going to get positive 3 lambda, right? Right, positive 3 lambda plus lambda squared plus 2 is equal to 0. You're going to notice that this is a certain type of equation. I'll give you a moment to think about what type of equation it is. It's a quadratic equation, right? It's a quadratic equation as a function of lambda, okay? And since it's a quadratic equation as a function of lambda, we want to put it in highest degree polynomial first and then lowest degrees, so forth to the right, okay? So this can be written, it's better to write it like this, lambda squared plus 3 lambda plus 2 equals 0, where lambda is a variable, okay? Right? The next step, right, which you should know from your linear algebra classes, is we need to factor. So if we factor our quadratic equation as a function of lambda, we get lambda plus 1, okay, times lambda plus 2, and this is all equal to 0. Each factor multiplied is going to be equal to 0, right? So we either have, we use another page here because I'm running out of room. Okay, you'll notice that we're going to have lambda, right? Lambda is equal to negative 1, and lambda is equal to negative 2. So you'll notice that both of the eigenvalues are negative. So what does that tell us? Well, it tells us that the system should be stable, right? There are some um, parameters, I won't say parameters, conditions, sorry. That's the right word. Conditions, to be more precise. There's certain conditions that tell us whether a system is stable or unstable. That's dependent on the determinant and the trace of the matrix, the 2 by 2 or n by n matrix that we have here. Okay. So because of that, that's why we have our matrix actually being stable, right? If you don't know what I'm talking about, please refer either to your course material if you're in a differential equations course, or you can look it up. It's very easy to figure out. You can just check the trace and the determinant and see what's happening. Okay. All right. So you'll notice that both are negative, so the system's stable, and which is correct because it's correct, but it's still incomplete. Okay, it's not good enough. Okay. Now I'm going to highlight, I'm going to say we're going to move to step 2 now. Okay, we're on to step number 2. All right, so step number 2. Okay, so step 2. Now for step 2, we need to determine the eigenvectors. Okay, so we need to find eigenvectors for each eigenvalue. Since we have 2 eigenvalues, we need to find 2 eigenvectors. So we need to find, so I'm going to say here, we need to find eigenvectors. Okay, so find the eigenvectors for each given eigenvalue. Okay, so I'm going to put over here so we have case 1. Case 1 is when we had lambda 1 eigenvalue, lambda 1 equals -1. Okay, for each eigenvalue, we're finding an eigenvector. So at lambda 1 equals -1. So we just put it into our equation. Okay, and our equation to determine eigenvectors, you should know, is that a minus lambda I, okay, our corresponding lambda value was lambda 1, lambda 1I on parentheses times the eigenvector v1 is equal to 0. Okay, that's the equation to determine eigenvectors. Now we just input the information. Lambda 1 we said was -1, so -1 times -1 is positive. I'm left with a plus the identity matrix times, what was it? We said v1, I believe. Yeah, it was v1. v1, and this is equal to 0 on the right-hand side, the 0 matrix. Now, what we end up doing is we're supposed to do RREF. So RREF. What does that mean? That means we're doing a row reduced echelon form. We reduce the matrix by Gaussian to a Gaussian matrix. Okay. Okay. So that's what we have to do. We have to do row reduced echelon form. Okay. And from RREF. Okay. So from RREF, so we're going to apply RREF. Okay. You notice that we're going to get something like this. Okay. We're going to get a matrix that looks like the following. Okay. So this is, just one sec, my pen is acting a bit weird. We're going to get 1, -2, 1, -2. Okay, that's going to be our RREF matrix. Now from that, that's to give us what the eigenvector is. Okay, right from here, right from this guy right here, our eigenvector after the row reduction. Okay, so it'd be v1. Eigenvector could be written as a column vector in terms of v1 and v2. v1 and v2 are the unknown variables of the system of equations above from the RREF. Okay, so then we're going to get v1 being 2, 1. Okay, 2, 1. All right, so we figured out what our first eigenvector is. This is my first eigenvector. Okay. Okay, I know can be a bit monotonous, but we need to get to case 2. I think you'll be able to understand what's going on here, right? It's just using from case 1, right? We had lambda 1, okay, eigenvalue 1 to get corresponding eigenvector. Then we're going to do case 2 for eigenvalue 2 and get a second eigenvector. Okay, so let's do that. So case number 2 now. Okay, so case number 2 is when we had eigenvalue lambda 2. Lambda 2 is equal to -2. Okay. All right, so we got this guy right now. Now, what we're going to do is, again, we have to set up an our eigenvector somehow. So we have to use, it's going to be A plus 2 times the identity matrix times the eigenvector V2, okay? And then this is going to be equal to 0. All right. It's pretty interesting stuff, all right? Now from here, after row reduced echelon form again, so we want to do RREF, right? In other words, RREF is this Gaussian elimination. If you forgot how to do Gaussian elimination, go back to your first year linear algebra, or sometimes I teach linear algebra in high school, end of high school, so you can refer to those books if you forgot how to do Gaussian elimination. I'm going pretty fast. All right, so RREF, okay. After row reduced echelon form, okay, I'm getting this matrix. I'm getting 2, right? So get 2, -2 in the integers in the first row. Then the second row will be 1, -1. Okay, all right, which means automatically, right? This automatically implies that my eigenvector, right? Remember, your eigenvector is found by getting the RREF, and then from the RREF you can get a system of two equations with two unknowns, V1 and V2. Solve for V1 and V2 as a system of linear equations. From there, from substitution, you get your eigenvectors, right? So V2 here, and it will be just 1, 1. Okay, I hope that's helping. All right, so we've got eigenvector V2 now. Yay. So we have V1, V2. Okay. Now we have two eigenvalues and two eigenvectors. Okay. Two eigenvalues and two eigenvectors. That's good because we want to have the same amount for each. So the general solution, right? So thus, I'm going to write here, thus, the general solution, okay, just give me a sec here, solution for our ODE, okay, for our ODE is written in this form, right? It's x as a function of t, where x is a column vector, right? A column vector as a function of t. T is a parameter, which is equal to c1, constant c1, which is arbitrary, times e to the negative power of t, right? Because lambda 1 is, just -1. It's positive 1, sorry, positive 1. So that's why I put here negative t times the column vector of 2, 1 that we found above. That was v1 plus coefficient 2, constant 2, sorry, times e to the power of -2t. Lambda 2 was, I said it was 2 somewhere. Let me see. Yeah, lambda 2, right? So lambda 2 was -2. That goes over here. Lambda 1, as I said earlier, was -1. Okay, that gets substituted for the first product of the exponential raised to the power of -t, right? To e to the -2t times the column vector of 1, 1. Now, okay, many people and students stop here, okay? They stop here and they say, okay, now it's all done, right? I'm finished, okay? Here's the actual mistake. The mistake is thinking that this algebra tells you, in terms of the applications, right? Tells you the dynamics of the system. It doesn't, and it doesn't fully, okay? I'm going to show you what I mean by that it doesn't show you the entire dynamics of the system. So if we go here to this mathematical model or simulation that I've made, okay, it's very detailed. You see the linear system x prime is equal to matrix A times x, okay? And what you'll notice, right, is that we're going to have two eigenvector directions right on the screen here. Okay? We got two eigenvector directions on the screen. Okay, and you'll notice that trajectory there. Something interesting happens. Okay, point P, that little dot there, I'm going to call point P, is following that trajectory, and it approaches the origin along that curve there. Okay, right, so if you paid attention to that, don't worry, this simulation goes on for a little bit. It's a pre-recorded simulation. Right? Based on the two eigenvector directions, the solutions are decaying, right? But the direction of the decay, right? The direction of the decay depends on how the eigenvectors are interacting. Okay, right. So the direction of the decay is going to depend on the eigenvectors. Okay, if the if the initial condition, let me just rewind here so you can see what I mean, right? And I'll pause. Okay. See lambda 1, lambda 2 eigenvalues with a particular eigen direction. So each eigenvalue has an eigen direction or eigenline that you can see there, right? As you can see here, there's eigenvalue 1, lambda 1 with eigen direction going upwards towards the origin in those arrows there with the eigenvector. Okay, all right. So if the initial condition, right, if the initial condition aligns with V1, the decay is slow and the rate should be -1. Okay, I hope that makes sense, right? Right, and if you align with V2, right? So if you align with V2 now, look at line 2. This shows lambda 2, -2. If aligned with V2, the decay is now even faster, right? It decays even faster according to the simulation here. Okay. Now, most of the initial conditions are just combinations, right? In other words, what I'm saying is that initial conditions are just a linear combination, right? That's what our solution to this differential equation is, a linear combination, right? Which I showed you earlier, right? X of t is c1 e to the negative t times v1 plus c2 e to the negative 2t power times v2. Okay, so again, just watch the trajectory of that curve there, and the point particle, the orange particle following that trajectory going towards the origin is aligned with both the eigenlines 1 and eigenlines 2. Okay, let's go back to the whiteboard. That is making, I hope that conceptually is bringing things home. That's what I'm trying to help you guys with, right? Right, so early time behavior may be dominated by a larger coefficient, but the late time behavior actually is dominated by a slower, the slowest decay, sorry. Okay. Right, so back to this guy here, right? Remember, this is representing V1. If you don't know, this represents V1, eigenvector V1. This represents eigenvector V2. Okay. All right. And the late time behavior is dominated by the slowest decay, as I mentioned, right? I just want to make sure you're understanding that. Now, the stability of this system, right, is going to tell you where it ends, right? Like where the trajectory ends. Okay, I might refer back to the simulation again to show you geometrically what's happening. Because if I just talk and you just see the algebra, you won't see what's happening. Okay, right? But the eigenvectors are going to tell you how it moves, right? That's why I brought up that simulation there to geometrically show you what's happening with point P, that orange dot, point P moving along the orange curve or the orange trajectory right there, right? Because the eigenvectors will tell you how it moves along the trajectory, which is I wouldn't say tangent, that's not an accurate word, which is going through the eigenlines. Okay, those eigenlines look like they're touching, right? Which they are, but the trajectory is going through the eigenlines back to the origin. Okay, and that's the most important thing that a lot of people miss is the behavior of the system. Okay, right. Now, let's continue with the geometry of the system, okay? So let's go back to the mathematical model. Just give me a sec. Go back to the white over here, okay? Now, I'm going to fast forward because I want to bring a point home, right? And the point is, okay, is that you'll notice that the arrows are converging towards the origin, okay? Notice how they're converging here. Hopefully you can see my mouse around that close to the origin, right? I'm emphasizing that just to say that the system's moving. The system does not move straight towards zero, but it's bending towards the slow eigenvector direction. Okay, there's a difference, right? The system doesn't move towards zero, but it bends towards the eigenvector. Okay. In other words, how would one represent that mathematically if it's moving towards or bends towards, right? You would say as t is approaching something, t is approaching infinity here, right? So as t approaches infinity, since we have a linear combination of our exponentials as our solution to the ODE, then that means that e raised to a negative power of anything has to approach zero because it's an exponential decay. Okay. And it's approaching zero faster than e to the negative t. Okay. And this model proves that. Okay. So eventually all the trajectories, I mean all of the trajectories will align with the eigenvector v1, which is the column vector 2, 1. Okay. Now this is just a structural insight on what's happening, right? The slowest eigenvalue actually dominates the behavior. Okay? So again, what I'm saying is that the eigenvalue that has the slowest rate, okay, right, will dominate the long-term behavior of the trajectory. Okay. And if you ignore this, actually, you're going to lose qualitative marks, right? If you just finished with that equation there, like the linear combination that I wrote for the solution of the ODE, it's not enough. You have to be able to sketch the trajectory like this. You have to know what type of trajectory it is, what type of phase portrait. That's the word, right? We're dealing with phase portraits, okay? All right, so phase portraits. And the phase portrait is very important, okay, to understanding the behavior. If you don't know, if you ignore this information, you're going to lose a lot of marks, okay? So let's get back right to the whiteboard, okay? So what am I fixing here? What's the point of this? What am I really fixing conceptually here? Why should you care as a student about this lecture? Well, the mistake I'm fixing is this. I'm treating the matrix ordinary differential equations as algebra instead of geometry. Okay? That's what I'm fixing. Okay, because the eigenvalues are equivalent to stability rates, right? All these eigenvalues. Okay, all these eigenvalues and their eigenvectors represent the flow directions. I think you can agree with that, right? And the dominant eigenvalue will dictate the long-term shape, as I mentioned in the simulation. This is what exam questions are testing when it comes to ODEs, and more specifically, phase portrait ODEs. Okay, not just basic determinant calculations. That's nonsense. Okay, so a phase portrait interpretation. Okay, I want to get to that. And a phase portrait interpretation explains all trajectories. Okay, so let me just write here. Let me just write here. This is very important. Phase portrait. So phase portraits. Phase portrait. Phase portraits. Phase portrait interpretation. 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 All right. Is that one? Is that all trajectories go to the origin? All trajectories? Trajectories. Trajectories. Up go to origin. To origin. Okay. There's no spiraling. No spiraling. That means real eigenvalues. Okay. This means real eigenvalues. Eigenvalues. Okay. No repeated eigenvalue issues. That's another note. No repeated eigenvalue issues. And then finally, no defective matrix. Okay, so there's no defective. It's going to be any defective matrix whatsoever. So no defective matrix. Okay. This is a stable node with only two distinct decay rates, as I've shown you. Okay. So if you can stay that confidently on an exam, you're not just guessing anymore. Okay. You're actually understanding the entire behavior of the system if you follow my procedure here when it comes to phase sports for solutions of ODEs. Okay. All right. So I hope that this has helped you conceptually understand phase portraits of ODEs. Okay. And I want to mention something that's important here, a confidence builder for you, right? So if linear systems have ever felt mechanical or confusing, okay, it's usually because no one's explaining the structure. And what I mean by the structure is the geometry, like I showed you with the simulation in detail and how the geometry is moving and the trajectories and all that stuff. Okay. So once you see it, the anxiety disappears, right? That's the thing though that a lot of people don't understand. Math and physics is more than just equations. You actually have to see, you have to see it. You have to see the phenomenon, the behavior, right? If you don't see it, it's hard to understand the abstraction. Okay. So you actually have to see what's happening. You're not behind, you're just missing the structure. Okay. That's what I'm pointing out in my video. Right? So if linear systems, um, sorry, if you want this level of clarity, right, when it comes to calculus or ordinary differential equations, I also teach physics as well, right? I tutor students who want structured understanding and no shortcuts when it comes to these topics, okay? The links will be below in at the end of this video if you want to inquire more about tutoring. And I've also, if you want this level of clarity when it comes to calculus, ODEs, or physics, I've written a book called Advanced Integration Techniques for Undergraduate Students, right? Where calculus and some ODEs, it's mainly calculus, um, come together in mathematical methods that are shown in some physics applications. Okay. All the links will be below in the end of this YouTube video. Okay. And I hope you've enjoyed it for all the subscribers. Don't forget to like and subscribe. And I'll see you in the next problem. Have a great day, guys.